welcome everybody to our last day of the Jones Memorial Conference. So let me welcome M.Khovanov, who will speak about facets of Temperley-Lieb algebra.
Oh, thank you, Anna. Am I supposed to use? I guess I can just use my microphone. Thank you. Thank you. Now, this is a sad, this kind of sad conference for all of us in quantum topology. So my encounter with work of Vaughan Jones happened very early on. I was an undergraduate at Moscow State University. I was interested in topology and low-dimensional topology, so I read about the Jones polynomial. And of course, the definition is beautiful, and it's also deceptively simple, because it's just a scaling relation, but it happened to hold always, and there is a unique solution to that scaling relation. But then you quickly learn that it has very rich properties and sophisticated structure. Back at the time, when I learned about Jones polynomial, one problem I was trying to solve was to take the scaling relation, Jones scaling relation, or related relation of Lewis-Kaufman, and see whether for links in a homotopy-free sphere, for instance, I was trying to prove that if you have a homotopy-free sphere, which is not a standard free sphere, that the scaling relation will give you a scaling module of infinite rank. But I mean, nothing came out of it. But later I learned that Joseph Shititsky also thought about exactly the same problem. Today I'd like to talk about various variations of the Temperley-Lieb algebra. And Temperley-Lieb algebra, I think it came to prominence essentially starting with Vaughan Jones' work, and it plays a central role in Vaughan's discoveries through, first of all, his connection between the Temperley-Lieb algebra and subfactors. And of course, when you start investigating the Jones polynomial, you immediately encounter the Temperley-Lieb algebra as a certain quotient of the Hecke algebra. And you cannot avoid it when you're working with the Jones polynomial and its extension to tangles. And so advancing his discoveries, Vaughan Jones developed this very general setup of planar algebras that includes Temperley-Lieb algebra as a very special case. And he also wrote papers on many variations, including annular Temperley-Lieb algebra. So it was really essential to his discoveries and his work. And I'll tell you, this is not a new story. It's many years old. I'll tell you, just review clarification, a particular clarification of the Temperley-Lieb algebra that's behind the clarification of the Jones polynomial. And then I'll tell you about a recent work joined with Robert Logwitz, where we use universal construction and interesting observation that by joint functors that we often encounter in quantum topology, they can be interpreted, or they can be related to some generalization, some version of the Temperley-Lieb algebra. So I'll talk about these two topics. A quick reminder, so Temperley-Lieb algebra is the algebra of planar diagrams with n bottom and n top endpoints. It has a basis of crossingless matchings of these two endpoints. It has generators we call UI, shown at the top with defining relations written down here. So we evaluate the circle to what's often called a T. And from the viewpoint of representations of quantum group, we usually write this as plus or minus Q plus Q inverse. These are the standard relations, standard defined relations for the Temperley-Lieb algebra. And one way to think of it is a quotient, as a very small quotient of the Hecke algebra of the symmetric group. And the Jones scaling relation is shown here. So later one can trace it to the intertwiners between representations of quantum SL2. And then there's a natural generalization where you change from 2 to any n. And when you put, instead of 2, you put 0, you get the Alexander polynomial. The case of 1 is trivial, 2 is the Jones polynomial, and beyond this it gets in some sense more complicated, with 3 and higher being the Kuiper bracket and more general SLN invariance, but introduce a different kind of complexity to the story. And of course, so one way to see that this is well defined is using the Kaufman scaling relation that also shows you the way the Temperley-Lieb algebra enters the story here. And all of these relations, if you think of it from the view of representations of quantum SL2, you're saying that the space of intertwiners between the second tensor power of the fundamental representation of SL2 is two-dimensional, so there's always a scaling relation on 3 intertwiners, and specifically the one shown here. And in general, when you have a so John's polynomial, when you extend these two tangles, one canonical extension is using representations of quantum SL2, where to endpoints on a plane you assign the nth tensor power of the fundamental representation of quantum SL2, and to a tangle T you assign an intertwiner between tensor powers representations. Intertwiner, let me call it f of t. And this assignment f is a monoidal functor from the category of tangles to the category of quantum SL2 representations. And in fact, so in graduate school, I studied this in a lot of details. So I guess I had propensity for topology. I ended up with Igor Frenkel as my graduate advisor, who was very heavily algebraic. So I was trying to find something in between, and it ended up being interactions between representations of quantum SL2 and topology, links nodes. And so an very interesting development, important development happened in 1994 in the work of Louis Crane and so back in 94, there was a paper by Louis Crane and Igor Frenkel on clarification conjecture for Wittgenstein-Reif manifold invariants. And I guess I interacted a lot with Igor during and after their work on their paper. So the idea that Igor was advancing during those years was that there's this new geometric representation theory that was a spectacular development, starting from the work of Kazhdan Lustig and Kashevara and other people on the canonical basis. And Igor observed, Igor pointed out many times that various constructions in geometric representation theory, they point to the existence of a structure one level up above representations of quantum groups. So in particular, there was this work of Bidinson, Lustig, and McPherson, where they realized quantum SLN by looking at correspondences between partial fact varieties and counting points in these correspondences over a finite field and computing compositions of correspondences. So surprisingly, you could see quantum SLN in the language of correspondences between partial fact varieties. And there are many other examples. There are other papers in geometric representation theory with a similar spirit. So a related question of Igor Frenkel was or his conjecture was, one should be able to clarify Schur-Weyl duality, which is the duality where you have, you take Cn, you add quantum parameter Q, which could be a generic complex number, and then on V tensor n, you have two commuting actions, an action of a Hecke algebra. Hecke algebra acts, sometimes it's a faithful action, sometimes it's an action through a Schur quotient, and you have a commuting action of quantum SLN. Here again, this is a Q deformation of the standard duality, of the standard Schur-Weyl duality for the action of SLN and the group algebra with symmetric group. So the figure pointed out that in V tensor n you have the weight decomposition, and then you can identify, you could see various weight spaces. You can identify them with Grothendieck groups of categories of sheaves on partial flag varieties. And that was, of course, the setup of geometric representation theory. So his idea was to try to kind of just repeat or rethink the constructions of geometric representation theory using kind of more functorial language, because in geometric representation theory, the emphasis at the time was on, for instance, study the canonical basis that emerges out of simple pairs sheaves. So the emphasis was different, but Igor's emphasis was on just understanding the whole structure together. And so what came out of his ideas was a joint paper where we found a lifting, a clarification of this data. So here you have a vector space with two commuting actions of algebras. So the idea was to look for, let me see. So the idea was to replace vector spaces or representations with categories and replace actions of algebras with actions of monoidal categories. And so we managed to do the simplest non-trivial case. This was a joint work with Joseph Bernstein. So we did the case when, notice that there are actually two n's here, capital N. That is the parameter in SLN. Here they take capital N to be a Q. And there is the lowercase n, this n. So if you specialize to SL2, you get a commuting pair of USL2. We did the non-quantum case. There was no Q. And the Temperley-Lieb algebra. And so if you try to do sheaves on flag varieties in a less technical case using more elementary representation theory, you discover that you need to work with so-called category O. Category O is built out of modules that are called Verma modules, some standard infinite dimensional modules over SLN. So here you need to take SLN and look at certain infinite. So to realize V tensor n as the Grothendieck group of an interesting category, you end up to, even though you start with representation of SL2, you need to do something unusual. You need to take SLN over all n and look at what's called a regular. You need to look at blocks of category O for SLN. Again, without going into technical details, these are certain categories of infinite dimensional representations of SLN with examples of modules that are Verma modules. So they have most objects that are infinite dimensional modules. But you can show that this category is equivalent to a category of modules over a finite dimensional algebra. So what we did, we picked up a collection of pieces called blocks of that category, such that the size of the Grothendieck group of this block is n choose k. N choose k is the dimension of the corresponding weight space of V tensor n. So V tensor n has a weight space decomposition with weights from you can label them from 0 to n, one dimensional in degree 0, n dimensional in degree 1, and so on with dimension n choose k in when k. And then so we picked the so-called singular blocks whose size is exactly n choose k. So these are so-called sk times s minus k singular blocks of O. And then on these blocks, there are so-called translation functors. So translation functors are summands of the functor of a tensor product with a finite dimensional representation. So here you're working with infinite dimensional representations, but you can take an infinite dimensional representation and tensor with the finite dimensional representation. And because you have a block decomposition, that functor on the category O ends up having lots and lots of summands, lots of direct summands. And you can look at summands and you can look at what they do on Grothendieck group. of the category. And it's easy to compute because the Grothendieck group has a basis of Verma modules. Verma modules, so they just give you a basis of blocks of category O. So everything is easy to compute, and when you look at particular translation functors, you see exactly the action of generators of SL2 on the corresponding weight spaces on V tensor M. And then you can ask about, what about the commuting action of the Temperley-Lieb algebra? Well, it turns out they're given by so-called Zuckerman or Bernstein functors, and you need to take the derived functor to see it. So we were kind of able to see both sides, both actions, but you do need to pass to the derived functors for at least one of them. And we also did the dual case. Instead of so-called single block, we look at parabolic blocks. Parabolic blocks of O, these are generated by so-called parabolic Verma modules. You need to take a Verma module, and you need to mod it out so that the resulting quotient module is locally finite dimensional. So it's an infinite sum of finite representations of the diagonal subalgebra SLK times SLN minus K. And again, you can match it so that the size of the Grothendieck group is the right one, and choose K. And then you take the sum over all K. And you get a causal dual story where on the sum of parabolic blocks, Temperley-Lieb algebra now acts by translation functors. So the role of the functors is switched. In the second case, it's sort of the easier action is Temperley-Lieb algebra action by translation functors, while the SL2 acts using Zuckerman-Bernstein functors. So we get two categorical realizations of this Schur-Weyl duality of the dual pair. But so later on, people looked into the story much deeper. Let me cite the work of John Grekier and then later work of Aaron Loudon in the SL2 case, where what one can do, one can look at, take these functors, say E and F, look at their compositions and ask what kind of natural transformations there are between the compositions and what relations do they satisfy. And when you do this, eventually you encounter a beautiful structure, and I refer you to Aaron's papers on this. It's a beautiful diagrammatical calculus for intertwiners, for homes between compositions of these functors E and F. And let me just remark for future, for later in our talk, that these functors E and F end up being bi-adjoint, which is part of the structure. But there's much more. So again, back then we did just the case of Q equal to 1, but in fact this parameter quantum Q parameter, it becomes a grading shift after greification. So it's not very complicated extension, but it adds extra rigidity and structure. And we still don't have a full understanding of what is the categorical meaning of this what's the categorical lifting of Q when it's root of unity. So we have an idea, we have a very good idea what to do when it's root of unity of prime order, and then we need to work in characteristic P, so everything is in characteristic P. But I think in general it's still unclear what would be a good reification of in characteristic 0 of the root of unity Q. But let me follow this story. And again, so the technical details were non-trivial because you have to work with category O, so you need to know a fair amount about category O, about functors there. So in particular, to get the factorial Temperley-Lieb algebra action, at some point we had to use, because it changes the number of strands. You go from n strands to n minus 2 when you factor the U diagram for the Temperley-Lieb algebra into a composition of a cup and cap diagram. Let me, if I can find this So maybe let me just say that it's still quite non-trivial because you need so you need a lot of technical details about category O, even in the special case when the blocks are relatively small. They're very degenerate. They have size n choose k. But at the same time, it turns out that you can actually do things in a more topological way without invoking a specific realization of this categorical structure. You can just guess what the category should be from a topological viewpoint. So first of all, let me just discuss it on the level of a Temperley-Lieb algebra. We can write Temperley-Lieb algebra as the algebra of endomorphisms of V tensor n of this representation of quantum SL2. We can write it as a space of invariants in V tensor 2n over the same algebra. So we're just using the fact that V is self-dual, so it's isomorphic to V star. And this space has a standard basis of crossingless matching. So it's an example of a crossingless matching for n equal to 5. So there are 10 endpoints, and we match them in pairs using arcs. And so this is a basis of a vector space. And various actions from which you see the Jones polynomial and succession to tangles are obtained by so they're obtained by acting by Temperley-Lieb algebra generators, or by braids, or by tangles at the top, just concatenating with elements at the very top. So maybe this is a smaller an example of basis element of invariance for n equal to 3. And so the idea is that before clarification, this is a vector in the space of invariance. So after clarification, it should become an object of the category. And this object conceptually should correspond to this collection of arcs in the plane. So of course, when we have objects in a category, we need to describe interactions between the objects. So we need to say what the homes are between two objects. And each object is going to be given by a collection of arcs in the plane. So you can guess that interactions between the two objects should be given by object in one dimension up. So we should look at cobordisms between two such collections of arcs subject to suitable relations. And this is what it turns out to be. And I'll give you, so we should come from cobordisms modular relations. And the kind of topological approach is kind of this sort of cobordism modular relation. So it's sort of like skein module, but for surfaces embedded in R3. So this was developed by Dror Bar-Natan. Again, this is not a recent story. It goes back a while ago. So you need skein relations on surfaces embedded in R3 to describe homes between two such objects. And let me tell you the same story, but a little bit more algebraically. So for every crossingless matching, we want to have an object. Again, so we're clarifying, so instead of a vector, we want an object. Let me call it P sub A. And in fact, this object is going to be a projective module over a certain ring, which I call H upper n. And, should be Hn. So the ring itself is going to be sum of these modules over all A's. Whenever you have a decomposition of the unit element as a sum of orthogonal idempotents, one sub A in a ring, you can always write the ring itself as a sum over projective modules, this ring times the corresponding idempotent, sum over all idempotents. So this is just what happens here. So our ring, misprint should be Hn. It's going to be sum of projective modules. Overall, B upper n stands for the set of crossingless matchings of endpoints. So, crossingless matching. And so the idea is that before codification, you can hide the minus sign in the Temperley-Lieb algebra relations. So you can just say that circle is Q plus Q inverse. And that, so after codification, this Q plus Q inverse becomes two-dimensional graded vector space with generators with basis elements in degree 1 and -1. And you have additional structure in this vector space. So you pick a commutative Frobenius algebra specifically of rank 2, because you're lifting Q plus Q inverse to a graded vector space. So we have a ground. We work over some ground field or in K, and we form the Frobenius algebra A, this one. So there are some variations on this Frobenius algebra, but for this to work, you want a rank 2 commutative Frobenius algebra. So out of this algebra, you get a two-dimensional TQFT with multiplication, co-multiplication, unit-co-unit maps corresponding to standard cobordisms between collections of circles. There's some kind of minor technical detail that such a commutative Frobenius algebra gives an oriented TQFT for oriented surfaces. And here everything is in fact embedded in free space, all the surfaces embedded in free space, and they inherit orientation from the embedding in the free space, where you need to alternate the orientation depending on how deeply you nest the surface. And so you take you can form the TQFT that assigns to a circle the corresponding tensor power of A. And from this TQFT, we're going to build a ring Hn, where these pictures correspond to projective modules. So the idea is you can take two crossingless matchings, A and B, with the same number of endpoints to n, and define the home from projective modules Pa into Pb to be this TQFT F evaluated on the gluing of A and B. So we reflect B about the horizontal axis to get B bar, and the composition AB bar is now a closed so it's now a closed one manifold, and we can apply the functor F to it, and this F is going to be tensor power of A in the number of circles. And to build our ring, we just take the sum of this Fs over all crossingless matchings A and B in Bn. Sum. So it's sort of so this is something that can be done in greater generality, but here there are more steps later on. But so we define homes between objects with boundary by gluing them along the boundary and applying the functor to that gluing. And so what is the multiplication? So let me now describe multiplication. Notice that the ring Hn is just the sum of these Fs over all A's and B's. So we need multiplication. That's going to be union of local products where you pick three diagrams A, B, and C, and you want to multiply f of B bar A with f of C bar B to f of C bar A. So you just need to cancel B against B bar. So let's look at this in more detail. So we have three matchings A, B, and C. A, B, and C. So we reflect B composed with A, reflect C composed with B. And now there's a canonical cobordism into where we match B against B bar using a collection of saddle cobordisms, one for every pair of opposite arcs in B and B bar. And so here we get identity cobordism in the middle. We can construct it to get AC bar. And so this is our multiplication in Hn over all A, B, and C. And then you can easily see that you get an associative unital ring. There's additional grading. And the unit element in Hn is given as the sum of idempotents 1 sub A. And the idempotent 1 sub A is obtained by, so for each A, take a bar, take this collection of circles, given by gluing A to A bar. And f of this is A tensor n, 1A for every circle. And you can just take the unit element there, 1 sub A, just 1 tensor n in A tensor n. And this idempotence, and the sum is the unit element. So in this way, we get an associative unital ring. And of course, you can do this construction much greater generality. But it's really useful in this case when we do this in 2 dimensions for algebra, Frobenius algebra of rank 2. And now you can extend the story to flat angles. So take a collection of arcs in the plane with even number of endpoints at the bottom and top, and define a bimodule over H and HM by just looking at all the ways to, let me scroll down a bit, look at all the ways to close T into a collection of circles by using a crossingless matching at the bottom and a crossingless matching at the top. Okay, so form a closed one manifold and apply F here, and take the sum over all A's and B's. And you can check what you connect by HN by changing B's here, by doing cobordisms that potentially change B, and a commuting action of HM by applying cobordisms that change A. And in this way, you get a bimodule. And you can check that everything works. So composition composing the tangles, concatenating tangles, corresponds to the tensor product of bimodules. And furthermore, so to a flat angle, we assign a bimodule, and to a cobordism, so cobordism between tangles. So now we are in 3D. We have a flat angle at the top, tangle T2. We have a flat angle at the bottom, tangle T1. And given a cobordism, so suitable surface with boundary and corners S, you can check what, you can kind of glue attach cross-linguist matchings times the interval on both sides. And this gives you a map of bimodules from bimodule for T1 to bimodule for T2. And all of this fully compatible with all kinds of compositions. So you get a two-functor from the two category of surfaces with corners in R3 to the category of bimodules. And so and in this way you get a sort of a clarification of the Temperley-Lieb algebra. Now, because of a construction, we need to have even number of endpoints at the bottom and top. So if you happen to have some number n of endpoints which might be even or odd, you can just complete it to even number of endpoints by adding dummy strands and work with the resulting diagram. And in this way, from every basis element of the Temperley-Lieb algebra, you can assign corresponding sort of thickened element and the corresponding bimodule over HM. So now you have realization of the Temperley-Lieb algebra basis by bimodules. And the composition corresponds to tensor product of bimodules. And every time you see a circle, you see a copy of the ring A. So you can remove it and say, I have two copies of bimodule assigned to whatever is left of my diagram. But so far, there was no homological algebra. But turns out, in the examples that we see in dimension 4, somehow to get invariance in dimension 4, we seem to need complexes. We need to have homological algebra. So homological algebra here appears at the last step, where you now pass from flat angles to arbitrary tangles. And again, so we are in the story, in building this invariance of links, we break in the symmetry. We break in the symmetry of R3, so we need a planar projection of the link. So in particular, so at the dinner yesterday, George told me that he still doesn't understand link homology, and we discussed this, and I agreed with him that we don't have a fully conceptual construction, in the sense that this approach and most other approaches, they require symmetry breaking, choosing a projection from R3 onto R2 to build complexes for links, tangles, and so on. And so here again we in this particular approach, to build invariance of links, now that we deal with arbitrary tangles which have crossings, we resolve a crossing. So what we're doing, we're lifting the Kaufman-Skin relation to the categorical level And instead of saying that this tangle is a linear combination of these tangles with simple coefficients, plus or minus power of q, we assign to this tangle a complex of bimodules. Bimodule for this flat tangle C0, going into bimodule for the flat tangle C1, using the most obvious map induced by the cobordism between C0 and C1. And you can check that at this stage, it's crucial that our Frobenius algebra has dimension 2, because to have the invariance under a Demeister 1 move, so if you were to close this up using a curl, close this up, you want to have invariance under this move, and for this you forced into Frobenius algebra A of dimension 2. And of course, there are very few such algebras. And if you want to do high dimension, this becomes an incredibly sophisticated story, where instead of a Temperley-Lieb algebra, you need to work with so-called Murakami-Atsuki-Yamada planar graphs, and then you want to build a vector space for every Murakami-Atsuki-Yamada graph, and that gives a different additional layer of complexity, and sort of that's a separate kind of sophisticated and long story. So what happened? We lift the Temperley-Lieb algebra one dimension up. So now to a flat angle, we assign a functor given by a bimodule over a very specific, very particular ring, and given a cobordism between flat angles, so given a surface with boundary and corners, to it we assign a map of bimodules. And everything fits into a 2 functor. And then there's this additional step, because so far this particular ring Hn and bimodules over it give us invariance of flat angles and cobordisms between them in R3. But to go to the 4th dimension, we have to start doing homological algebra, and we have to form complexes and cones of the map. Take cone of this map. And sort of fancy extensions of this to SLN and to SLN invariance, they require working with, instead of planar diagrams of the Temperley-Lieb algebra, you have to work with certain trivalent graphs, MY graphs, and then you need to get invariance of cobordisms between these graphs, which forms, and this is, so again, this is kind of adds more complexity. And so this way, so what we went very briefly over this story, but you get, so this way you get a clarification of a Jones polynomial. So for a link you get a complex of graded vector spaces. If you take homology, you get bigraded homology groups whose only characteristic is the Jones polynomial. But this approach allows you to extend it to tangles and to tangle cobordisms. And if you'd like to see this story and some variations of the story stated in less algebraic language, I refer you to Drawer's work, where you don't need projective modules, you just work with categories and objects of the categories and corresponding complexes. But so in this way, we get a 4-dimensional TQFT restricted to surfaces in R4, and this is definitely a major obstacle so far that people are trying to deal with. So how do you extend to beyond surfaces embedded in R4 to 3 and 4 manifolds, to homology of 3 manifolds, to invariance of surfaces in 4 manifolds? And so we heard a very exciting talk by Paul yesterday on, about the recent advances in that direction and what can be done. But so far we have the most clear understanding for links in R3, link cobordisms in R4, and this theory is best understood when your D algebra is SLN, so you're clarifying SLN quantum invariance. And the best understood case by far is when you're clarifying exterior powers of the fundamental representation of SLN. So this is the minuscule case. beyond minuscule, things become much harder. And again, so on one hand, if you look at this algebras Hn, so the Grothendieck group of Hn, it can be identified with a space of invariance of tensor power of the fundamental representation. But if you play around, you can pass to subquotients and you can calligraphy the entire weight space. And then people discover that you can, the same algebra, same category, can be located in many different places. So I can refer you to the work of Kamnitzer and Kautis, who found essentially the same structure inside derived categories of coherent sheaves on quiver varieties and inside derived categories of coherent sheaves on suitable convolutions of affine Grassmannians, orbits of affine Grassmannians. So people have found, again, it often takes a big effort to prove that you get the same story that you get on action of tangles, factorial action of tangles, and so on. But so you can locate this in Fukaya Floyd categories associated to certain Springer fibers. So this is work of Seidel and Smith and Abu Zaid. You can locate this throughout representation theory in many ways. So the same kind of categories, they sit inside many different representations of interest that appear in algebraic geometry, in symplectic topology, and representation theory. So on one hand, you have a strong connection to those fields. On the other, you get highly non-trivial invariance in dimension 4. And this is something that we knew since the work of Jacob Rasmussen, who found the commutable proof of the Milnor conjecture using this homology theory, but also referred to to remarkable recent work of Kyle Hayden and Isaac Sandberg, who checked that the invariance you build this way, the invariance for tangle cobordisms. And the invariant of a tangle cobordism is a homomorphism between homology groups assigned to links. So they check that this invariant can distinguish certain surfaces embedded in D4 with the same boundary, a particular node, and the surfaces are homeomorphic, REL boundary, but not diffeomorphic. And so many years ago, these surfaces were distinguished using Donaldson invariants by Selman Akbulat, and that was about 30 years ago. So it's sort of interesting that on one side you have representation theory, category O, or modular representation theories. Again, the same categories sit out in many locations. You have algebraic geometry of derived categories of coherent sheaves and suitable quiver varieties, but on the other side you have invariance of smooth structures in dimension 4. It's a very interesting, so the same structure, the structure connects different fields in an interesting way. So let me tell you briefly the second story. So this is something that I found very, very interesting. So you can relate versions of Temperley-Lieb algebra to pairs of bijoint functors. So you can find this in the recent work with Robert Lagwitz. But of course, this idea goes back many years. This suggests that if you have two categories, A and B, if you have two functors, between them f and g, of course, we all know and love adjoint functors f and g. And then if they're unjoined, you can check what this is equivalent to having suitable natural transformations between compositions of these functors and identity functor. And these transformations can be drawn using string calculus in the plane, where regions of the diagram correspond to categories, category A, category B. Sequences of points in a line correspond to composition of functors, and pictures inside correspond to natural transformations. And here we're drawing natural transformation using cup and cap diagrams, transformations between FG, GF, and identity functors in this way. And then the condition that the functors are adjoint are equivalent to the condition where exist these two transformations such that these diagrams are equal. These two diagrams are equal, this diagram equal. So you can recognize isotopy invariance in the properties, in the adjointness property for this pair F and G. But you only see 1/2 of the isotopy relations, because you can also reverse the orientation and swap labels A and B of the regions. So to see full adjointness, you need to add the condition that they are adjoint on the other side as well. So you say then that you have a bi-adjoint pair. Functors F and G are adjoint on both sides, and adjointness are fixed. So these natural transformations are fixed. And you'll have 2 more of the transformations from the second adjointness. And then you have full isotopy invariance. You have four versions of this picture with different orientations, different A's and B's. And then whenever you have a collection of circles in the plane and you choose a label of the outside region, you then color the regions in checkerboard fashion, AB, ABA. And such a diagram gives you an element of the center of the category. An element of the center because in this picture, we don't have any starting or ending points. We go from nothing, from the identity functor on A to the identity functor on A. So this gives an element of the center of the category A. And center of the category is a commutative monoid. So you get these pictures giving you elements of the center as long as you have a bijoint pair, as long as you have a pair functor and a bijoint functor. And so you cannot just take a circle and pull out. You get a different element. So every nested combination of circles gives you some central element, and typically they're different, perhaps with some complicated relations on them. And if the outside region is labeled by category B, then you get an element of the center of category B. And whenever you have some diagram, C, with the outside region A, you can put a circle around it and get an element of the center of B, and vice versa. If you have an C prime, an element of the center of B floating, you can put a circle around it to get an element of the center of A. So you really have 2 commutative monoids, center of A, center of B, and you have 2 maps omega that have no properties whatsoever. They're just maps of sets. They don't respect multiplication. They're just maps of sets. So this is sort of an interesting structure. And it, of course, it's reminiscent of a Temperley-Lieb algebra, because it's also circles on the plane. You can add arcs with boundary. Then you'll have functors F and G at the top and bottom. But in the Temperley-Lieb category, we don't care about the nested structure. We can remove any circle, multiply by D. But here we do care about the nested structure. And another sort of interesting example where people care about the nested structure is in the work of Robert Lifshitz and Sushri Sarkar, where they constructed a spectrification of link homology. So they, instead of just complex of abelian groups, you get a collection of spectra, one for every degree. And in their construction, when they assigned some kind of a state space to a collection of circles in the plane, how circles are nested is important to them. So that's another example. It's a very sophisticated work. Goes back several years. But for them, the nesting of the circles is essential. But so here, this is, I think, this is a sort of underexplored structure. So a long time ago, Joseph Bernstein wrote a paper about this called tracing categories. But there has not much been done since then. So this is what it looks like in general. So we can, and multiplication in the center is given by placing the diagrams next to each other. And so I want to say this is sort of an example, to me it's sort of an example where you have a planar structure, you have a plane, and you have defects. You have circles that are nested in the plane, and you assign elements of the center of the algebra to them. So it's an example where defects naturally appear. So here I wanted to refer you to work of a, let me go to the linear case for now. Now that was very general, but often we deal with categories that are linear. So everything is k-linear over some field k, and the center of a category then is the commutative k algebra, and the maps omega between the centers are k-linear. And we looked at this case, at the situation in the work with Robert Logwitz, and we did to have less bookkeeping. We did the case when the categories are equal, it's the same category A, and functor f, it goes from A to A, and it's self-adjoint. So this just reduces the amount of bookkeeping. So then there is just one category, so every region is labeled A. And then to any such diagram of nested circles gives you an element of the center of A. And such diagrams they correspond to trees. To the outside circle is the top vertex of a tree, and then you depict nested, and that's by lines emanating from the vertex down to children of the vertex. So here there are inside the circle there are 3 more circles here corresponding to 3 nodes, and then inside, I think I made a mistake. I should have put an extra circle here to have two. So this is a misprint. I should add an extra circle here to have 2 nodes at the bottom. So any such diagram gives you an element of the center. And then the map omega, so you can take any diagram and put a circle around it, and that's just a linear map. It's not a map of algebras. And in our paper, we use this universal construction approach, that you need universal construction if you want to do link homology combinatorially beyond the L2 case. Somehow the most efficient known approach is using universal construction. So here, the idea of universal construction is that you only have data for closed objects, and from this data you build your topological theory for objects in one dimension less. So the way it works here, we hide the center of the category and we hide omega, and we assume that all we have is a map alpha, that starts with a diagram like this and assigned to it a number. So we implicitly assume that we have a trace on the center of an algebra into the ground field. In particular, this trace would take any diagram to a number. And we assume that that's all that's given. So you just have numbers for closed diagrams and nothing else. This is the setup of universal construction. And let me scroll back. So given such a variation of closed diagrams, we want to build state spaces in one dimension less. And the way it works here is the following. Let's take our diagram, and let's cut it by a circle into an inner region and outer region. And I'll take this circle. It consists of, inside we have some number of arcs and some number of circles, and we have even number of endpoints. So let us fix the number of endpoints to n, and look at all possible diagrams with these endpoints and anything inside, any combination of arcs and nested circles. And so let us look at all diagrams with 2n. Let me scroll back for a second. So let us look at all diagrams of this form for a fixed n, and first take any linear combination of these diagrams. So you get a very large space. In these linear combinations, let us introduce relations. Let us say that we have a relation sum of diagrams Ci, diagrams inside the circle, with some coefficients lambda I. This is equal to 0 in the state space if no matter what diagram we choose on the outside, any diagram C, and glue it to Ci and evaluate using alpha, the corresponding sum is 0. So we artificially introducing skein relations in our diagrams. We say that the sum is 0 if for any C, gluing C outside and evaluating using alpha and taking linear combination gives us 0. So this is how universal construction works in general. So impose these relations. I mean, we don't know what the relations are, but we just impose them. So we get a monoidal category. We call it C alpha. In this monoidal category, homes from n to n, from n to m, are given by looking at all diagrams, all pictures from n to m, closing them up, and just using these relations, using this construction, using these relations. So again, we don't know what the relations are, but we know they exist, depending on the properties of alpha. And then we usually want something small, so we say that alpha is a rational variation if the dimensions of the state spaces are finite for all n. And you can check that's equivalent to just the dimension of the n equal to 0 being finite. So n equal to 0 corresponds to no endpoints, just putting collections of circles here. And linear combinations are 0 if no matter what you put on the outside, and evaluate you get 0. And so we get some category. And in this category, the functor of tensoring with of adding a dot on the boundary is self-adjoint functor. And so in our paper, we've played with this construction. This is sort of an example of universal construction, and an example of getting a bijoint pair from this data alpha of evaluations of circles. And let me quickly point out why we care about bijoint functors. We care because whenever we have a TQFT in some dimension plus 2 with corners, and let's say this TQFT is categorically valued, so to n manifold we assign a category, to a cobordism in dimension plus 1 we assign a functor between the categories, and to a cobordism with corners in dimension plus 2 we assign a natural transformation of functors from functor for M0 to functor for M1 in the boundaries. And in this situation, always for any cobordism M, this pair of functors Fm f of M star, Fm star just the reflection of M, this is a bijoint pair. This is sort of the picture how to build these transformations. Take M and M star and just rotate M into M star to get M plus 2-dimensional cobordism. And this gives you, this cobordism now gives you natural transformation from identity functor from null to the composition of these two functors. And this is sort of what the isotopy relation corresponds to in the language of cobordisms. And it's not a big deal. It's hidden in the WRT theory in dimension 3 because everything is semi-simple, so everything is automatically has a bijoint, so it's not a big deal. But then it was a sort of hint where to look for topological theories. You want to look for categories which have an abundance of bijoint functors. So for instance, categories of matrix factorizations have this property that there are lots of bijoint functors in them, and categories of sheaves and Calabi-Yau manifolds. Whenever you have a Fourier-Mukai transform, between them there's a bijoint functor given by the dual transform. And okay, I'm out of time, but just want to say that this example with bijoint functors, we see some kind of defects appear in the plane, these lines that give us natural transformations between functor f and its bijoint. And these defects seem to be, again, I'm not a physicist, but they seem to be a common feature now in physical literature, but we also see them in these explorations of the universal construction of topological theories, even in very low dimensions. So, for instance, for topological theories in dimension 1, again, this is a separate story, a separate talk. So I just briefly mentioned that if you do defects, zero-dimensional defects for one-dimensional manifolds, and you do this over Boolean semi-ring, you kind of, what you'll see is some basic structure in computer science known as a regular language and automata. And you get a category that is a tensor closure, rigid tensor closure of regular languages and automata. And this is joined with meson in. And we did some exploration of the universal construction in dimension 2 in the work. Joined with Radmila Sajdanovich, Yakov Kanonov, and Viktor Ostrik, where we again, this is universal construction where you know invariance for closed objects, and you build invariance for objects in one dimension less out of the state spaces. And we recover modifications of the delinquent category of representations of a symmetric group in complex number of parameters, complex number of points. And I want to say that if you try to go one dimension up, it seems to be rather unexplored in, for instance, if you, so this collections of circles and arcs in the plane, they correspond to bijoint functors. So next level would be embedded surfaces in free space. This would be some kind of clarification of bijoint functors, and I think this is completely unexplored. And maybe related reason that it's unexplored is something that Lev Rozansky pointed out to me. If you want to build invariants of nested surfaces, for instance, using Chern-Simon theory, you need to have defects in Chern-Simon theory in dimension 2. And so Lev Rozansky pointed out to me that there doesn't seem to be such defects. The known defects are one-dimensional, where you have an embedded knot in the free manifold, and you take the monodromy along this knot as your observables. So you have observables for codimension 2 manifolds, but not for codimension 1 manifolds. So I don't think we have good examples of such variations of embedded surfaces in free space, for instance, from Chern-Simon theory. So this is specifically, we have lots of remarkable structures for links, but not for surfaces. Of course, you can take a link and thicken it to a surface, but you get a very special, very particular surface. So I think this seems to be an interesting question that's completely open. And again, I want to point out that there's kind of in these stories there are two steps. One step does not require homological algebra. You build some state spaces using universal construction, evaluations, etc. But later, to get to 4D, you need to pass to complexes, so you need to do homological algebra. So it's another interesting open problem if you can do this at once. And I think that's maybe another way to rephrase Dror's question about how to understand link homology more intrinsically without these steps where we first work in 3D, 2D, and there's no homological algebra. But eventually, we add complexes as the last step. And so these were two examples where we see variations on the Temperley-Lieb algebra. On one hand, we see its clarification. On the other hand, we see this modification where something similar to Temperley-Lieb algebra emerges from any pair of bijoint functors. And I'm a big fan of bijoint functors, and I think that's what we've understudied. We've been understudied so far. And so these are just sort of two examples to add to kind of remarkable work that Vaughan-Jones gave us, that of bringing Temperley-Lieb algebra to the front of the story. A very interesting story that involves so many structures. And again, we hope to look forward and to further develop his insights and just find more structure in high dimensions and kind of variations on Temperley-Lieb algebra ideas. And so this was sort of to give you to review two more appearances of the Temperley-Lieb algebra in today's quantum topology. Thank you.
Thank you very much for this nice overview. Are there any questions or comments?
I know you were going kind of quick at the end, but in your 2D cases, were you looking at defects in those examples, or?
Let me scroll back.
Yeah, just the 2D case. Oh, no defects. So the cases that you've studied so far involve no defects. But
Yeah, we'll look at
is it an interesting problem to have the defects in the 2D case?
So if you add zero-dimensional defects, you're adding points on the surface, possibly labels, and then points commute. So it's not too much additional structure. But if you add circles, one-dimensional defects, that's I think much harder to classify. I'm not sure that classify is the right word. You want to find interesting examples of that. For instance, using the universal construction. And here we're just doing the plane with circles. It's very specific to the plane. But you're seeing bijoint functors, and then if you're into computer science, if you do this planar story, you see some, in a set-theoretic case, you see some version of what people call tree automata. It's a variation automata where you kind of computing on a tree, because these pictures are like trees. But most general case would be a network of defects. So one-dimensional defects on the surface which are like diagrams in monolith categories, where you have vertices with edges coming in, coming out. And of course, this is very general, so I don't think any reasonable classification is possible, but you can ask for interesting examples of such theories and what applications to other branches of math and maybe physics.
For an adjoint pair, there is this associated monad. For this biadjoint pair, it will be, I guess, more special. So do you have a topological interpretation of this monad?
Yeah. So for adjoint pair, you can rethink of it using a monad, but here, yeah, it's sort of, I think monad would be oh, sorry.
Michael Muger studied when you have biadjoint pairs, how you get
that's probably
the
one.
monad is for, well, I think he wasn't calling it a monad, but I did this in my thesis also.
Yes, one reference. Yeah, it's sort of, well, in monad, so you just don't care about specific functor f and g, you care about the composition. You take composition of g, and you look at transformations between that. And you can do that here too. And you sort of, so you get both kind of merge and split. So you have a little bit like, so it's both algebra and algebra, but of course it's not a half algebra. It's maybe closer to some kind of Frobenius algebra then.
You get a Frobenius object in HOM AA.
Okay, thank you.
Okay, so if there are no further questions, then let us thank Michael again.